Ampere's law. Today we will discuss Ampere's circuital law, its integral form and its differential form, its applications in magnetic field near long straight wire, magnetic field of solenoid and magnetic field of toroid. And in the last we will discuss limitations of Ampere's circuital law. Ampere's circuital law says that the line integral of magnetic field along the closed path is equal to mu naught times current enclosed by the closed path. Mathematically, its closed integration vector B dot vector dl equals to mu naught I, where I is the current enclosed by the closed path. If path does not enclose the current, then closed integration vector B dot vector dl equals to 0. Ampere's law plays the same role in magnetostatics as Gauss's law plays in electrostatics. Differential form of Ampere's circuital law. In this figure, C is a closed path where current flowing, J is a current density and ds is a small element of surface enclosed by the path C. The total current enclosed by the path C is I, and I equals to surface integral vector j dot unit vector n ds. From the integral form of Ampere's law, we know closed integral of vector b dot vector dl is equals to mu naught I. Now substituting the value of I in the equation. So closed integral vector b dot vector dl equals to mu naught surface integral vector j dot unit vector n ds. This is our equation number 1. And in this way, area S is specifying the region through which the current exists, and unit vector n is unit vector normal to elementary area ds. Applying Stokes theorem, closed integral vector b dot vector dl equals to surface integral of curl of vector b dot unit vector n ds. This is our equation 2. From equation 1 and equation 2, surface integral of curl of vector b dot unit vector n ds is equals to mu naught surface integral of vector j dot unit vector n ds. Now comparing the both side of the equation, curl of vector b is equals to mu naught vector j, and this is a differential form of Ampere's law, and this is also one of the Maxwell's equation where charge and densities are constant and current are steady. So the electric and magnetic fields are not varying. It gives simple relation between magnetic fields and moving charge. Now applications of Ampere's circuital law. The first application, the magnetic field vector B near a long straight wire. Let us take a long straight wire and current I is flowing in it. The field lines of magnetic field B makes concentric circles centered on a wire. Due to symmetry, all points on the circle have same magnitude of field B. The angle between B and vector dl is 0. So vector B dot vector dl equals to BDL. According to Ampere's circuital law, magnetic field at point P at a distance r from the wire, closed integral vector B dot vector dl equals to mu naught I. Now in place of vector B dot vector dl, we will write BDL, as we know the angle between vector B and vector dl is equals to 0. So closed integral BDL equals to mu naught I. Taking out the B out of the integral, so B closed integral dl equals to mu naught I, and when we are integrating dl over the entire region, it is giving 2 pi r. So B 2 pi r equals to mu naught I. This gives you magnetic field B equals to mu naught I upon 2 pi r. That means the magnetic field due to a long straight wire by Ampere's circuital law is equals to mu naught I upon 2 pi r, and it is the same expression as we get in Biot-Savart law. The second application, the field of long solenoid. Now If a solenoid is very long as compared to its diameter, so the magnetic field inside it is much stronger as compared to the field outside it, and inside the solenoid the lines of magnetic fields remain parallel to the axis of. Now consider a rectangular loop ABCD which is lying half inside and half outside the solenoid. The line integral of B for this path will be closed integral vector B dot vector dl equals to integral AB vector B dot vector dl plus integral BC vector B dot vector dl plus integral CD vector B dot dl plus integral dA vector B dot vector dl. Now, from the figure, it is clear that magnetic field B is perpendicular to the path BC and DA. So, integral BC vector B dot vector dl and integral dA vector B dot vector dl will be 0. Now, the other part, that is integral CD vector B dot dl is negligible as compared to integral AB vector B dot vector dl, because the DC path is outside the solenoid and field outside the solenoid is very small as compared to the field inside the solenoid. Therefore, closed integral vector B dot vector dl equals to integral AB vector B dot vector dl equals to BL, where B is magnitude of magnetic field inside the solenoid and capital L is the length of solenoid. If there are capital N number of turns in solenoid and current I is passing through each turn, then the total current passing through the solenoid will be capital Ni. And from Ampere's law, closed integral vector B dot vector dl equals to BL, and this will be equals to mu naught capital N I. So B equals to mu naught capital N I upon capital L, where capital N upon capital L gives N small n, and that is the number of turns per unit length of the solenoid. So the magnetic field of the solenoid is B equals to mu naught Ni. The third application of Ampere's circuital law, the magnetic field of toroid. The toroid is a circular solenoid whose both ends are joined and the axis of toroid is circular. The magnetic line inside the toroid is also circular. From Ampere's law, we know closed integration vector B dot vector dl equals to mu naught I, and we know that angle between vector B dot vector dl is equals to 0 degrees. So, in place of vector B dot vector dl, we can write BDL. So, closed integration BDL equals to mu naught I and B closed integration dl equals to mu naught I. This gives B into 2 pi r equals to mu naught I and B equals to mu naught I upon 2 pi r. If there are capital N number of turns in toroid and I current is passing through each turn, then total current passing through toroid will be capital Ni. Then the magnetic field of toroid will be B equals to mu naught I N upon 2 pi r. Now the limitations of Ampere's circuital law. Symmetry is crucial for application of Ampere's law. Ampere's law is applicable only when there is a uniform and symmetrical current distribution and symmetrical Amperian path. The applicability of Ampere's law depends upon our ability to evaluate closed integral of vector B dot vector dl. When Ampere's law is applicable, it is the fastest method. But if Ampere's law is not applicable, then Biot-Savart law is the only option. Now these are the books for the reference. The first is David J. Griffith, Introduction to Electrodynamics. Then second is Electricity and Magnetism by Edward M. Purcell and David J. Morin. And third is The Fundamental of Electricity and Magnetism by Arthur F. Kipp. And Fourth is Electricity and Magnetism with Electronics by K. Tiwari, and the fifth is Electricity, Magnetism and Electronics by Ahmad and Lal.